class at 9 o'clock.
Yeah, that's why
Did he fall down a hole or something? We don't have to do any homework because we did the questions in class yesterday. So we just go straight into the final topic on materials, which is called Young's modulus. An interesting topic. I don't know if you've studied this before in physics.
It's stress over strength.
Yeah, you have studied it. You have studied it, yeah. So it's kind of interesting because you can work out how much an object will stretch. Important for engineering. Who's doing civil engineering? You're doing civil engineering, you think, and you're doing.
hopefully electrical.
Don't think it comes up in electrical, but it will come up for sure in civil engineering. You know, whenever you're dealing with constructions, you have concrete or metal, and you put weight on it, and then it compresses a little bit. You know, or like you're building a bridge.
The heat.
And the heat too, yeah. So it's very important for construction. Anyways, I don't think it's too difficult. I think it's usually a good question in the exam. So let's have a look. Young's modulus, if we can write that down, please. Yeah. Okay. Adnan?
Yeah.
Okay. Do you know this word, guys? Your English is quite good, so you might know it. Deformation of a material.
Form it more again, like deform.
Yeah, but try to explain deformation without using the word deform.
Broken.
Not necessarily broken. I know what you mean, but it's not necessarily broken.
Like making something from something else from a particular thing.
Or a nuclear bomb and so get broken.
Like from plastic you can make.
You're getting closer now to it. So when you say the deformation of a material, it's changing the shape of the material. For us, usually the length. By applying a force, stressing force. So for example here, if I apply a force, look, and, well, I broke it without breaking it. If I change the shape of it by using a force, you can say that I'm deforming the material. So deformation is changing the shape from a force. Okay. Got that? Yeah. Okay, so that's deformation. Now, stress, I know you understand the word stress. You look at your physics teacher and you think, poor man, so much stress. But there's a physics definition of stress as well. I wonder if any of you know the physics definition of stress. Because, Mir, you said earlier stress over strain.
Yeah.
So, do you remember what stress is?
I think one of them is like going in, and one of them is like.
What's the formula for stress?
Length over area.
You're half right. One of those terms is wrong. So stress is the force acting on the material per cross-sectional area. In other words, stress is force over area, which should remind you of something else that you... Pressure, yeah. So what's the unit for stress?
Yeah.
Yeah, so clearly the unit is Pascal. So that's the definition of stress. Got that?
Yeah.
Okay. Next. Strain. Mir or Adnan? No. Strain is defined as the change in the length, which I'll call x, that has taken place during the original deformation. So basically, it's how much the length has changed compared to the original. So as a formula, strain is just the extension divided by the natural length. Got that? Yeah. Did you say you did this before, stress and strain?
Yeah.
Did you? Yeah. And you did it before? Yeah. Yeah. Okay. So next. Oh, what's the unit here for strain?
No units.
Not meters?
No units.
No units. Because it's meter over meter. So no units for strain. Unit free. Okay. And you know this one, Mir, Young's modulus. Now, just so you know, I use the letter Y, but I think a lot of books use the letter, do you know? I think a lot of books use the letter E, but I don't like that because that looks like energy. So I use the letter Y. Although in the exam they don't use any letter, they just write down Young's modulus, so it doesn't really matter too much. So Young's modulus is defined as the ratio stress to strain, that is, stress over strain. You got that? Yeah. What's the units for Y, for Young's modulus?
Pascal?
Pascals, yeah. Okay. So, continue? Yeah. Tensile strength, is this a word someone might know? No. Tensile strength is the force you need to basically break something. So a rope or a wire, it's the amount of force you would need to snap it. It's like the limit, you know. So tensile strength, of course, is measured in newtons, or is it actually newtons per square meter? I'm not sure actually. Newtons, I think. But all you need to know is the word. You don't actually need any formulas for it. Yeah. Okay. Okay, let's look at a stress strain graph and compare it to an extension force graph. So, come on. It's frozen. Stress strain. Okay. So let's just here. This one here is stress, and this one here is strain.
See, how can we know that? Like, we have to write something in the y-axis or the x-axis?
Yeah, I wasn't clear with the way I wrote it. I should have written it like this: stress against strain, which is the y against the x always. It usually goes yx. Okay. So the next one then is extension force, for example, here. Or I thought last time, didn't I put the graph the other way around? Did we do this graph last time? Or am I thinking about the January students?
We did one graph, we said that, it's important.
What graph did I do last time? I don't remember.
Yeah, it was on
the what?
It was the other way around?
Yeah.
Okay. And then I'll need to change that. It was like this, is it? Yeah. Okay. So, do you remember what the slope of this graph was?
K.
It was K, wasn't it? Yeah. Now let's have a look at what we have here. So the slope would equal, remember, it's stress, stress over strain here. Yeah. The formula for stress is F over A, and strain is extension over natural length. Yeah. Now, you can change this into F. Let me think. A 1 over A over 1 over L times F over extension, like that. Yeah. This can be cleaned up as L over A times F over extension. Now, what is this though? If you look at this graph, what is this? Well, this is the K, isn't it? And what did we say the slope of this graph represents? What is stress over strain? Young's modulus. So what I'm trying to get you to see here is that there is a strong similarity between Young's modulus and the spring constant, the stiffness constant. So if a material has a high value for K, then it also has a high value of Young's modulus, and vice versa. So your interpretation is that, remember we said if the K is big, then it's not stretchy, it's kind of stiff. Likewise for Young's modulus, if the Young's modulus is big, we have the same feeling that it's a stiff material, not a very stretchy material. So I suppose all I'm trying to get you to see here, if you want to write it down, is that Young's modulus has a similar interpretation to the stiffness constant.
So,
no, you don't have to write all this down. I'm just trying to get you to see the link. This isn't even a formula in the course. I just want you to see that Young's modulus is proportional to the stiffness constant. But I hope you can also see that the difference, though, is that this also depends on the length and the area, whereas with the K it doesn't. By the way, I didn't actually say exactly what the area is. No, I mean what part of the, like if I have something like this and there's a force pulling on it,
cross-sectional.
it's which is what? Yeah, describe where that is in the picture though. Use words.
I think it's the end.
Yeah, it's this area here. Yeah. Okay. Can I continue?
Yes.
Okay. So I don't forget, let me add that in. So how does Y relate to K? They're proportional. Okay. So what we're going to do now is give you some values of Y for different materials. Come on, wakey. I had extension on the x-axis, so we usually write the y first. So I just need to swap them. Okay, let's have a look at some values here. So something that's really, really stretchy, like rubber, the Young's modulus is 0.10 times 10 to the 9. Nylon is also, they all look kind of big. I guess what I'm trying to say is usually the numbers for Young's modulus is quite big, because remember we said if it's very stretchy it should be small, and if it's very stiff it should be big.
Yeah.
So this is rubber. Is rubber stretchy or stiff? Stretchy. So this is small, although you can see how big it is. This is actually a small value for Young's modulus. So first one, rubber, 0.1 times 10 to the 9 pascals. Okay, so let's move up. Do you know nylon? Yes? Do you know nylon? Yes, yeah. So that's also stretchy, 2 times 10 to the 9. Yep.
Yeah.
Now we're starting to get to material which is less stretchy. Wood is a little stretchy because you can kind of bend it, you know. So that's 10 times 10 to the 9. Glass, now we're getting into materials which are not stretchy. Although glass is a little stretchy because you can kind of squish it a little bit. It's 70 times 10 to the 9. Next, brass. What is it? It's bronze. No, what's brass? I can't remember what's next up. It's an alloy.
Yeah, it's copper and
Copper, yes, copper and
aluminium.
aluminium? I don't think so. Iron? No. Do you do alloys in chemistry? Metal alloys?
I think we did metals.
Yeah, did you do brass?
Yeah, it's copper and zinc.
Copper and zinc. Okay. 100 times 10 to the 9. Copper, 117 times 10 to the 9. Steel, 200 times 10 to the 9. Graphene, 1050 times 10 to the 9. And graphene is the material in your pencil. And that's it. Okay, you got those? I have too much. There. Okay. Right, so here's our first example here. You don't have to write it down, you can just draw it. A boy hangs a 100-gram mass at the end of a 1.5 copper wire, which is attached to the ceiling. The wire is 2 millimeters thick. So you can write or draw it, but we'll do the question together. I might have one you can borrow. Okay, did you write this down, Mir? Adnan?
Yes.
Yeah. Yeah. Continue? Yeah. Okay. So let's have a look at it now. Let's see. It's 100 grams. It's copper. It's 1.5 meters long. Okay. So this, sorry, what did I say? 100 grams, so 0.1 kilograms, and the length from here to here is 1.5 meters, and the thickness 2 millimeters. And what was my first question? It was cross-sectional area. Okay, so you said the formula earlier, Adnan. What is it for the area of it? Yeah, the area is pi r squared. And what's the r here?
0.002.
Gotcha. It's half of this, because that's the thickness. The radius is half of this number. So it's 1 millimeter is the radius, which is 1 times 10 to the minus 3 squared, which is pi times 10 to the minus 6, which is 3.1415 times 10 to the minus 6 meters squared. So that's part A. Part B is stress, is it?
Yes.
Yeah. Stress is
F over A.
F over A. Now, what is the F here? What's causing the stress on the wire? Yeah, it's the weight. So that's mg over A. Well, we were getting worried. We thought we'd have to send people to search for you.
No.
We were thinking maybe you fell down a hole. No, what happened to you?
I missed the bus.
Really? That's so unlike you. Why'd you miss the bus?
Actually, I didn't miss the bus. I think the bus didn't come.
Oh, you're changing your story. No. You should always stick to one story with your teacher. The bus didn't come?
Yes, I went to the bus station and he didn't come, and then I went to another.
That's okay. We are doing physics, as you can see, because I was going to do maths, but these two people weren't in the last class, but they were in the last class for physics, so that's why I did physics instead.
Wow.
Well, not wow. Do you have your physics stuff with you?
Do we have physics today?
No.
I don't know.
You'll have to write in your maths book and copy it later then. Okay, what were you saying the force was, Adnan? The mg. Whoops. So that's 0.1 times 9.81 over 3.1415 times 10 to the minus 6. Syntax error. Oh.
Today.
No, I forgot my notes. 312 kilo.
What is the name of this
One sec.
Young's
Young's
modulus.
modulus. Here, Musharif. Young's modulus. So 312,000 pascals. Okay. Got that? Yep. Part C, strain. Now, we have this formula for strain, extension over natural length. Now, the problem is, we only know one thing in this formula. What?
Natural length.
The natural length. Do we know the extension? We don't have to. We can use a different law. We can use the formula that Young's modulus is stress over strain. Because we know Young's modulus for copper, I gave it to you. We've just worked out the stress. So the strain is the stress over Young's modulus. What is it for copper?
117 by 10 to the power 9.
Okay. .375 times 10 to the 3. That's the strain here. Have you studied this before? So this is all confusing. Great. Okay. Well, you're writing everything down? Okay. Continue. Now, what is the extension? So I can use this formula now because I know the strain is 375 times 10 to the 3. The extension is what we want, and the natural length is 1.5. Wait a second. Something went wrong here. My strain is too big. Oh,
It's over.
I have this upside down.
Upside down.
312,000 over, what was the
117.
117 times 10 to the 9? No, I'll just flip it around here. 2.67 times 10 to the minus 6. Okay. Strain equals extension over length. So that means extension is strain multiply length, which would be 2.67 times 10 to the minus 6 multiply 1.5, which is 4 times 10 to the minus 6 micrometers. So if you picture what's happening is you have the copper wire, the boy hangs something on the copper wire and it moves, it extends a tiny 4 micrometers longer. Okay. And lastly, the K. So you have F equals K delta X, or Kx, whatever letter you want to use. So K is F over delta X, which is mg over delta X, which is 0.1 times 9.81 over 4 times 10 to the minus 6, which equals 245 kilo newtons per meter. This is a typical exam question, which I actually think this question is quite good in the exam. It's not that bad. You're just really using a couple of formulas, which are quite simple really, the formulas, because they're all just fractions. Continue.
Are you doing the tutorial now?
I think we'll do the tutorial today as well. I think so. Because, yeah, we will. Okay. Next question. Just one more. 4 metal beams, 2 centimeters by 2 centimeters by 2 meters, are used to support a platform. The platform of mass 3000 is suspended from the beams. 1000 kilograms is placed on the platform. The beams extend a total of 2 millimeters. So let's do this one together. I'll try and draw it. You have 4 beams. Yeah. You know what I'm drawing. And they're all attached to a platform, and this hangs from the ceiling. And this platform, I said, is 3000 kilograms, and this then somebody puts a mass on it of 1000 kilograms. When you place the 1000 on it, it extends by, it gets basically 2 millimeters longer when you put the 1000 on it. What's the strain? What's the stress? What's the Young's modulus? Oh, so we'll start off with the strain. So what's the formula for strain? Yeah, delta X over L. So that's 2 times 10 to the minus 3, and what did I say the original length was? I think it was 2 meters. Originally it's 2 meters long. So that's over 2, so that's just 10 to the minus 3. So that's okay, yeah? Right, what do I want next? The stress. What's the stress here? Yeah, force over area. Now, the force is what? The weight.
1000 G.
Yeah, why not 3000 though? Red herring, yeah. It's a bit like, if you were to look, I can't remember if we talked about this, but anyways, if I go back to the graph here, this is stress, this is strain. Isn't this what we drew earlier? Yeah. So Young's modulus is stress over strain. So if there's already 3000 on it, or 2000 or whatever, and then you add more force, like 1000, the Young's modulus is just the difference in the stress divided by the difference in the strain. It's like the extra stress divided by the extra strain. Usually we start at 0, so it's the total stress divided by the total strain, usually. But in this case we're not starting at 0, but that's okay. We only care about the difference, which, so like you said, Mir, this 3000 is a red herring. So if I go back here, it's 1000 G over, and what's the area? 0.02 times 0.02 times 4, Y4. Or sorry, it's the other way, no, not 4 there. 1000 G divided by 4. Why do you think I'm doing that? There's 4 beams. So this is the force on each one individually. So what we're doing is we're just looking at one of them. So I'll divide this by 4. Okay. And it's 2 centimeters.
So why did you ignore that 2 by 2 meters? It's 2 centimeters by 2 centimeters by 2 meters.
Yeah, this is just the area though. No, you don't care about the length. It's the area. So that would be 250 times. One, two, three. 6.13 mega. What is the stress on each beam? Each beam has this much stress. C. What is Young's modulus? Yep. What's 10 to the 9? Giga. 6.13 gigapascals. Got that? Okay. And finally, how much more will the beam extend if there's another 1000 placed on it? So basically now you have 2000 on it. What's the extension? Okay, so we could use I think we could go with Young's modulus is stress over strain. because we know what Young's modulus is now, which is a constant. Stress is force over area, and we know the force and we know the area. And strain is delta x, which is what we want, over the original length. Yeah. Okay. So that would be, if I rearrange that, Young's modulus times delta x over L equals F over A. So that means delta x would be LF over YA. That's 2 times 2000 G over 4, because we're looking at one beam, over 6.13 times 10 to the 9 times 0.02 squared.
It's 12 or 10 to the 12? It's giga.
A giga is 10 to the 9.
Yes.
Yeah, it is, yeah.
So,
Yes? Yes. Two, yeah. Mm, 4 millimeters? Yeah, 4 millimeters. Now, I was being a bit sneaky here in this question. Guys?
Yeah.
I was being a bit sneaky. I said, how much more will the beams extend if it's another 1000 is placed on it? So this here is the extension for 2000. But I didn't want that. I wanted the extra extension after you put on another 1000.
It's only 2 millimeters.
So, huh?
2 millimeters?
Say again?
So it's only 2 millimeters?
Oh, you're halving it. Yeah, it could be, but we have to work out what the extension is when it's 1000. So it's done the same way, except what number do I change here?
1000.
This is 1000 instead of 2000. So this is when you have a force of 2000, and if you had a force of 1000 kilograms weight on it, then what would it be? It'd be 2 millimeters. So yeah, you're right, Adnan. It would just be the extension, which is extra, is just 2 millimeters. So what happens is, first it extends by 2, and then when you put another 1000 on it, it extends by another 2 millimeters. So the answer is 2 millimeters. Yep. Continue. Yeah.
okay.
Oh no. Okay, so I think I would like to do these today after you try them, and then that ends this chapter of materials, and then we have 2 chapters left, fields and atoms then. Do you think you can do these, or
Can you explain to me why they are doing this?
can I explain what?
Like you can plot the graph.
Yeah.
Explain to me the lesson from there. Why they are doing the story.
No.
Okay.
But it's good that you asked. What I'll do instead